In this video tutorial, we shall see how to generate delays using software instructions and how we can use those delays to generate a waveform. It may be a square wave or it may be a waveform of any other duty cycle. Let's say that the question is you have to generate a square wave of time period 10 milliseconds on some port pin, but the main thing is using software delays, right? And the crystal frequency given is 11.0592 megahertz, right? And it is not mentioned which timer to be used and which mode to be used. So you are free to use any timer and any mode, right? So it's up to you, right? So for that, first we have to see what is the delay we have to plan. So the time period, the total time period, that is this total time period is 10 millisecond. That's what is given in the question. T is equal to 10 millisecond. And because it's a square wave, so the on time and the off time, so this is the on time, this is the off time, will be equal. So T on and T off, right? So both will be 5 milliseconds, right? Right. So we have to design a delay for 5 milliseconds, right? And most of the students, they do the mistake for designing at 10 millisecond. No, we have to design for 5 millisecond, and this we have to generate on P1.0, right? And what is the logic? The logic is relatively simple. First, make P1.0 high, right? And it has to remain high now. After going from 0 to 1, it has to remain high for 5 milliseconds, right? So now you give delay of 5 milliseconds, so that after making it high, so that will remain high for 5 milliseconds. Once 5 milliseconds has elapsed, now you make it 0, right? So make P1.0 low. And now it has to remain low for how many milliseconds again? Again 5 milliseconds. So again call a delay of 5 milliseconds, right? And after this, the process repeats, right? Now the main thing is to design a delay of 5 milliseconds using software instructions, right? Now how do we do that? For that, we should have a base code, okay? We should have a base code. You can have your own base code, right? So whatever the code I have put in the lab program, the same I am putting. Let me call the delay as delay, right? And I am putting a count, move r2 comma hash count. I don't know how much count has to be put, but I'm planning this, okay? What I'm planning is I'm writing a base code for 1 millisecond, right? And I will introduce a NOP instruction, NOP. Then I will decrement the count, dj nz r2 comma back, right? So that back label will be here. At last, I have to return from the subroutine. So this is my base code, right? One can have his own base code, right? Based on that, this count value will change. So the total delay what I want is 1 millisecond from this. Fine. Now each instruction takes some time, and the time taken by each instruction is given by the number of machine cycles. Okay, what is a machine cycle? It is the time taken by the instruction to execute. Okay, move instruction, it takes 1 machine cycle, right? And knock instruction, no operation, also takes 1, and this knock also takes 1. Decrement jump on non-zero, this takes 2, and the return instruction, it also takes 2 machine cycles, right? Now what we are supposed to do is we are supposed to calculate this count now. Okay, what should be this value so that this delay gives me a delay of 1 millisecond. Okay, so the given crystal frequency, okay, it is 11.0592 megahertz. Fine. So this is the crystal frequency. So therefore the machine frequency, it will be 11.0592 megahertz divided by 12. So it comes out around 921.6 kilohertz, right? So therefore one count will be 1 upon 921.6 kilohertz. So that turns out to be 1.085 microseconds. It means what? The minimum time which is taken for the execution is 1.085 microsecond. It means if you say that my instruction takes 1 machine cycle, it means it is taking 1.085 microsecond, right? Now we need to calculate how much, calculate the value taken. We need to calculate the value to be loaded here so that this generates a delay of 1 millisecond. So for that, first we need to calculate the time taken by this back loop. Okay, this is the inner loop, if you see, right? First we will do this. Okay, so for that we can write as time taken by back loop. Okay, it is equal to time taken by the first NOP instruction, right, plus the time taken by second NOP instruction, right, plus the time taken by DJ NZ instruction. So these are the 3 instructions which are coming in this loop, right? The first NOP instruction, the second NOP instruction, and the third is the DJ NZ instruction. And these 3 instructions are executed how many number of times? This count number of times. Because we don't know that, I will write it as X. So all these 3 instructions, right, they are executed X number of times. X is nothing but that count, right? So how many machine cycle the knob takes? It takes 1, and 1 count is 1.085 microseconds plus 1 into 1.085 microseconds plus the time taken by this is 2 into 1.085 microseconds multiplied by X. So if you compute this, you will get 4.34 microsecond into x. So that's the time taken by back loop. We don't know what is x. Now what is the total time taken now? That is the total time taken by the delay subroutine. Total time by delay subroutine. So that will be equal to the time taken by move instruction, right, plus time taken. We have already calculated the time taken by the back loop, right? So the total time taken now will be the time taken by this move instruction plus the time taken by this back loop, which I have already calculated, right? So time taken by back loop plus the last instruction, that is time taken by the return instruction. Time taken by return instruction, right? So the time taken by move instruction is 1 into 1.085 micro plus the time taken by this is 4.34 microseconds into x plus time taken by return is 2 into 1.085 micro, right? And what is the total time we are planning? We are planning for 1 millisecond. Okay. So if you compute, so you will get x is equal to 229.66. Okay. So this x is nothing but the count. So I will approximate this to 230. Okay. So the count which has to be put in decimal is how much? 230, right? So if you convert this into hexadecimal, it will be E6. So if you put a count of 230 here, so this base count will give you a delay of 1 millisecond, right? Now the question is, we want a delay of 5 millisecond, then why did I plan a delay of 1 millisecond? The answer is, if you know the base code, right? So we can call this base code any number of times to achieve the required delay, right? Now we are supposed to, so the required delay is how much now? 5 millisecond. Okay. How do we achieve this? So we will call this 1 millisecond code 5 times. That's it. Let's say for some other program you have around 10 milliseconds. So in that case, we will call this 1 millisecond code 10 times. Okay. So that's why you have to remember your base code. Okay. So if you remember the base code for 1 millisecond, you can write the code for any number of milliseconds. Okay. We shall program the same now. Right. So this I am planning to display on P1.0. So move P1 comma hash 00h P0 as output port, right? Now we know the logic. We need to make P1.0 high. Set bit P1.0, right? So this will make high, and we have to call delay. Then I will say clear P1.0. I will again call delay. Delay of how much? Delay of 5 milliseconds. And here also delay of 5 milliseconds, right? And this I have to repeat. I will say jump repeat. So this is the repeat which will generate the required square wave, right? Now here I have to write my delay subroutine for how many millisecond? For 5 millisecond, right? So here I will write delay. So first you can write the code for 1 millisecond. Move, let's say R2 comma hash 230, right? Then knob DJ and Z R2 comma back. So this code is for 1 millisecond, right? But what is our required delay? It is 5 millisecond, right? So this code, if I repeat for 5 times, so this will provide me a delay of 5 millisecond, right? So for that, what should I do now? I will initialize one more register with hash 5, right? And I will repeat this entire 1 millisecond code 5 times. So DJ and Z R3, comma, let's say back 2, back 2, right? Now this will give me a delay of 5 milliseconds, right? And at last write return. Fine. So let's execute this. We may not get an exact delay. Why? Because the return instruction is excluded now, right? The return instruction is excluded actually. So that's why we may get some microsecond error, right? So let's execute this. Now to view the output, we need logical analyzer. So go to view and click on analysis window and click on logic analyzer. Okay. First we need to set up this. Okay. So go to setup, and because we are displaying on port 1, type P1. Okay. How to type? You can see this icon, click and in capital type P1. Okay. Then select that P1 and change the display type as bit. Okay, and you can select any color which you want. Okay, let it be as it is and just close it. Right, now this program should provide you a square waveform of 10 how many milliseconds? Yes, 10 milliseconds, right? So let us run this now. So you can see we are getting a square waveform, but we don't know what is the time period. Okay, you can scroll your mouse button to increase or decrease the time period, right? So what you should do is you should first stop this. Okay, then this cursor will be unselected. You select this cursor. Okay, and I want the time period for 1 cycle. So this is the rise time. So I will click here and you just go on moving here. Right, now see here it is displaying the time period. You can see here adjacent to 400.5433, you can see the delta. Okay, what I will do is I will capture this and I will paste here. 1 minute. I will capture this. See here. If I keep now, if I paste, oh, it's not getting captured. So it is 10.04666 millisecond, right? So we have got approximately 10 millisecond, right? So this is how we generate the required delay using the software instructions. Thank you.